So today we have our PhD track talk, and I would like to invite our guest, Hasan Abu-Rasheed. He's from Goethe University, Frankfurt, and he's working there as a postdoctoral researcher. So I would like to invite Hasan to give your talk.
Thank you very much, and thank you for being here. I'm glad and honored to be a part of this conference and to be a part of the doctoral consortium as well with this invited talk. This is because I'm not far from finishing my PhD beginning this year, so I do remember the pain of the PhD finalization. And it is a real honor to recap all these years that we have been doing research on, which I am going to do today, to talk about AI responsibility, AI interpretability, and how we can actually provide system or design systems from the beginning to be interpretable and explainable at the end. And what is the role of neurosymbolic AI in that process? So our line of thought for today will be basically starting with our motivation and breaking down the problem that we have been trying to solve for the past 7 years. And spoiler alert, it's not solved yet, but I would like to share with you how we approached that solution during those 7 years and how we used the knowledge representation and transparent data structures to approach that problem solution. I'm going to go to use cases that we have been working on amongst several use cases during the past 7 years, focusing on an industrial perspective and a pure academic perspective. However, both of them are in the educational domain. So we have industrial knowledge transfer in training process of new engineers, and we'll highlight vocational education and training in the nursing domain. Then I'm going to talk a bit about neurosymbolic AI and how we approached actually building a system that combines both advantages and tries to reduce the disadvantages of both worlds. From that approach, our aim is to reach explainability of these systems and enabling thus not just an explanation, but a user of making an informed decision. That's our ultimate goal, the user at the end, to make an informed decision about the predictions from the AI systems or AI supported systems that are providing recommendations, providing grades, and so on and so forth. And we will recap by some conclusions and some takeaways. So, a little bit about me, to have a background about this research. I'm working as a postdoctoral researcher in the Goethe University in Frankfurt. And my stay is basically providing AI systems for teachers and learners in the university, whether they are students or external students and so on and so forth. So the employees, the teachers, and the learners on an administrative, teaching, and learning levels. And in this, we are investigating the role of then semantic web, semantic technologies, and chatbots in supporting our target group in higher education. My PhD was concluded in computer science in the University of Siegen, also in Germany. Not very well university in a small city called Siegen. And the topic was adding context and explainability to context-aware recommendation systems. And the way I approached this in the PhD is using Markov decision processes over knowledge graphs. And so you will see that those terminologies will repeat consistently and frequently in this presentation: recommendations, explainability, context awareness, knowledge graphs, and I will not go so much about Markov decision process because I'll just highlight it quickly. I'm also very honored to be a member for some years now in the Association of Technology Enhanced Learning, where I joined through the ECTEL conference, if you haven't, if you haven't or have been someday. And also a part of the organizing team of the EATAL Joint Technology Enhanced Learning Summer School. And I wanted to highlight the summer school specifically because if any of you has PhDs or is a PhD student and working on educational technologies, perhaps the summer school would be something for all your PhDs that you are supervising. I have been in the summer school around the middle of my PhD several years ago. And it was 1 week of extensive exchange on technology-enhanced learning. It adds so much perspective from multiple disciplines: curriculum design, technology developers, psychologists, philosophers, and so on and so forth, on the supervisor level, of course. So maybe you can also join, check it and join. Recently, I also had the pleasure of joining the European Digital Education Hub through an Explainability in Education squad, where we worked on providing or producing a report, which has been published just last week, actually, officially, and it's about explainable AI in education, fostering human oversight and shared responsibility, in which we look at explainability from 3 directions: from pedagogical direction, technical direction, and legal perspective as well. My current focus is supporting, as I mentioned, the agency of educational stakeholders in making decisions based on AI predictions. So being supported by AI and not being guided or misguided by that prediction. My main focus at the moment is also conversational explainability, which I will come to at the very end. So what is the problem? Why do we even need explanations? Basically, as you all know, developed technologies have or pose a lot of risks. One of the very common examples is how LLMs hallucinate, for example, generate misinformation. They are fed some misleading data intentionally or unintentionally in order to generate wrong answers, and that is actually has an effect, or that has an effect in real life. We are witnessing now papers that are completely made up when we do scientific research. We are witnessing facts that are completely wrong and made up by wrong data or by hallucination through the model biases and so on. When we talk about the bias problem, we are actually covering a wide spectrum of biases. We have biases from the data, we have biases from the model itself, we have biases from a social perspective, and it's the box of Pandora of these problems when we talk about the bias. And unfortunately, those biases are present very much in large language models, and not only the large language models, which gain their reputation as tools we use every day just several years ago, but there are also predictors that have use in real life for more than a decade. And this have been studied in several occasions, and several surveys have been conducted to address if they can provide predictions that are fair enough or that can be counteracted if they are misleading, and so if they are wrong, can be found if they are wrong, and so on and so forth. And it has been found that there are so many types of biases that we actually can hardly detect before even thinking of counteracting those biases in the models. One of the nice books about it is this Weapons of Math Distraction. So the pun is intended here. And it talks also about the role of algorithms in guiding our thinking, not only as individuals, but also as societies, which is very critical and very catastrophic to some extent when we talk about situations like the war. So we talk about these biases and we read papers about them, but are we affected by them? Have we actually been losing something because AI is biased? Is our salary less? Have we lost a dear one because of AI biases? Well, unfortunately, the answer to these questions is yes. We are being directly affected, not only by the biases, by the misleading information, as has been also covered in the brilliant talk yesterday. And we're seeing more and more real life effects, which affects our jobs, affects our lifestyle, affects the way we can trust the tools that we are using. And so, unfortunately, the answer to this is yes. Some examples, not only from the LLM, but from 2012. Some teachers have been assessed through their student feedback, and some algorithms in Washington public school, some teachers have been actually fired because of these evaluations. and labeled as, okay, they are not very good teachers because the evaluation from their students was low, or the performance of their students was low. But that overlooked, or the algorithm has overlooked completely, the differences between the classrooms. Some of the students had special needs, some of the students had difficulties in learning, and that affected their teachers' evaluation. Now, one can say, okay, we can actually find out about it, we can ask the teachers, but no. Unfortunately, from a social perspective, from our behavior as users of AI-supported technologies, the school trusted the algorithm more than the teacher. Because actually investigating this means spending more time, putting more effort, and they thought, okay, the algorithm says so, we just fire the teacher, end of story. And the teacher appealed, but the appeal was dismissed. Other teachers have faced also a similar situation. At the moment, we are seeing a burst in the amount of CVs provided to companies. Those in industry perhaps can also relate to that point, because CVs are generated easily through AI generated tools, through LLMs. And HR departments are not able to cope with the huge amount of CVs, and therefore automatic filtering is now getting more and more used, and not just trusted, but inevitably used in our hiring processes. And therefore, people are actually losing jobs just because their CVs are not even considered for being reviewed. They are completely filtered based on some terminology they have used, or the lack of certain terminology, and so on and so forth. So yes, this is affecting our lives. Can we mitigate that effect somehow? Well, to mitigate that effect, we need to understand not just the size of that, but also the different dimensions of the problem itself. And when we talk about biases, when we talk about algorithmic misinformation, the predictions that are not factual or counterfactual at some point of time, we talk about different types of disciplines or dimensions or fields that affect or feed that problem. One of them is the biases itself, and we have different types of biases. We have the biases, we have the social biases, etc., data biases, and so on and so forth. That's not everything. That's just the technical part of it. We have a social part, we have an economical part, a legal part, and several others, which I did not add on the slide, but they are there. In the economical part, we talk about the revenue produced by those models. We're talking about the push to generate a financial outcome. We're talking about the monopoly of those models, monopoly of the data. The companies that have scrapped, stolen, or collected data with or without our consent, and now it's being used for those models. We're talking about accountability from a legal perspective. Who is responsible for generating a wrong prediction or a wrong answer? Recently, Meta had faced a huge scandal, maybe you have heard of it, because their chatbots were allowed intentionally to conduct romantic discussions with children, with minors. And it doesn't find that in the system rule base, it was actually intentionally allowed. It was not allowed in the sense they wanted it. It was not prevented. So they did not explicitly prevent a chatbot to conduct this type of intimate conversation with a minor or a child. And they justified it by the fact that they have reviewed those rules. This is something OpenAI also did. And they have asked people to see if the rules are okay or not. And people said, or majority of the people said the rules are okay. So we have audacity now from those monopolies to actually justify this misbehavior. And that's something completely different from biases, but we are facing it also in our daily life. We have the over-reliance from our side as users. It is easy to generate my CV through a chatbot or an LLM. It is very much easy to write an essay if I'm a student and I'm running out of time and I have a deadline tomorrow. It's very easy to think with a chatbot, but now we are seeing psychological effects of that use, which students are actually starting to not believe that they have to think about a certain problem. And this has been studied in the recent paper on programming tasks. And several students have been given a certain programming task, and they were divided into groups. They were allowed to use resources, including chatbots, or based on their own study programs, like what they have learned in schools. And at the end, it was found that those who used a chatbot, they finished the tasks quicker, they got higher grades than those who the effort. But then after a while, asking them after a week or 2 weeks or what they did back then and how they solved the problem, it was those who actually in the solution that remember what they did. And that affects now the hiring itself. So if I finish my task in a job interview very quickly, should I be hired now? Or should I finish the task not perfectly and need more time because the company actually use my experience because I'm using my own knowledge? So the over-reliance on technology is also affecting how students are thinking about learning, the goal of learning, and why they are actually bothering to write an essay in the first place if a chatbot can write an essay. And those are not easy questions. These are fundamental questions about why we learn and how we convince our children to actually put the effort in learning if they are not seeing a result from that effort, or at least not seeing it on the short term. So AI is generally leading to less understandability, or these problems are generally leading to misunderstandability of the models themselves, where the problem is coming from, and then less ability to make a decision about it. Should I put the effort in it, or should I just use a quick tool and get a good grade? So we tried to analyze this, and this is the breakdown of the problem that we have tried to do over several years, trying to approach it by understanding the mechanisms of actually making that decision. If our goal is to enable a user to make a better decision, a more informed decision, then how do humans make the decision, and how can it be supported by AI and not hinder it? So we try to study making the decision indexes of clarity for information available through AI to those users who are making the decision. Actually introduced an index to show how transparent AI systems are to different types or different groups of users. And we defined 3 tiers of transparency. Those systems that are transparent and understandable by highly experienced people, developers, highly technical backgrounds, and so on and so forth. There are the second tier are the edtech experts. So they have an idea about technology, but they are also coming from an educational perspective. They are not developers themselves, but they understand technology. And this tier actually enables them to understand how the predictions are generally formed, how the system is generally, without understanding the details of how deep neural networks work and how Markov decision process functions and what is reinforcement learning, and so on and so forth. This is the actual teachers, students, and the public. And it means that a system belongs to that tier if it's understood by everyone. For example, if I have a decision tree, simple if-then rules. If I come to a conference, I have the chance to attend presentations, wonderful presentations. If I go to the beach, I have the chance to go and swim. Perhaps if it's raining, maybe swimming is not, so on and so forth. So this is understandable to everyone. The problem is that when they try to analyze AI landscape in terms of to which tier those systems that are available in our daily life, to which tier they belong, very, very limited amount of papers and AI systems belong to tier 3. Some of them, much less than expected, belong to tier 2, and the vast majority of AI solutions that we have belong to tier 1, which means that only those who develop them and are on the same level of those developers can understand what's actually happening. And that is alarming. That's alarming because we need at least tech experts to make a decision, because those are the ones who are making sometimes decision if a tool is bought and licensed for a university or a school or not. They are not the developers, but the administrators. So this means that at some point of time, we reach a level where AI systems provide us with some predictions, but we are unable to comprehend those and make a decision based on them. And this is a caricature that I have seen in around 2017. And since then, it actually which now sounds funny even to me, shaped how my PhD worked out from a caricature. So I don't actually, I guess the Paul is the one, so I'm actually grateful to him. So it says that this cup is asking if someone is cannot or not able to read. Does your car have an idea why my car stopped it? And at some point, we need the technology to tell us what to do and why there's some prediction happening, because why would we think about it? So analyzing this problem and breaking it down to its main components, we actually ended up with this representation. The problem that we are facing, those technologies depending on AI, is actually a problem of knowledge transfer. AI models are trained on data, especially stochastic models that have a lot of input data, running statistical training processes so that they can generate a prediction, which is how the neural network is working. And so the data is generated by data producers or information producers, data sources, let's call them the sources. And those sources, some of them are informed, some of them are like teenagers writing something on Facebook. This data is collected. They don't have experience, they don't have an idea if this is correct or wrong, but this data is collected. And all of this data is fed then to automatic algorithms with complex processes models this data, processes it, and makes a prediction out of it, whatever the mechanism of making that prediction. And then provides this to the actual users or the target of this data or knowledge transfer. Knowledge is being transferred. This is us, the normal users, or children, daily life users. The idea is this path here has a lot of potential risks. And those risks come from the way knowledge is represented, which is interpreted not only by the end users, but also how this model understands the input data, or interpret the input data, and how the knowledge is actually being processed, what technologies are used to process the information, and how these technologies are working, and then the decision making, which is at the user side. So I tried to depict, non-systematically, but based on all this research through the 7 past years, which potential risks exist. And there is a risk in collecting the data itself. The biases in collecting data from majority of English language literature in comparison, in contrast to Ukrainian literature. This is a risk that lies in the data collection itself. There is a bias in the way data is being prepared for the models to be trained. So this transfer of data, where is it stored? Is it stored securely, or is it leaked? Does it contain sensitive information about the users or not? And there's a lot of risks that are being at the moment handled on also governmental levels for data security, data centers, localization of AI models, and so on and so forth. There's a risk in the way those models interpret the data. What does it mean for a model to interpret the data? Let me give you an example from last week. Last week, we have launched a chatbot tool internally in our department for testing. This is a normal practice that we do before offering this tool to the whole university, so that we can collect preliminary user input, an alpha test, where we do some refinements on the chatbot before we actually making it public for the university itself. One of our colleagues in the department has a German Italian, and he was testing the chatbot. He asked a question in Italian language. The answer from the chatbot came as follows, and I quote literally: "I understand your question, but I only answer in German language. If you wish, I can give you the answer in German language, or you can ask in German language." My colleague was furious. He said, "No, this is discriminatory. How could this even happen?" And I was like, really, what the hell is happening? I mean, we have never taught the model to use a certain language. We use prompts to control it, but we never actually explicitly mentioned the language issue. So we reviewed all what's happening in the backend and our prompts to actually which was our try to enhance the accuracy of the answers, to make the model provide answers that are suitable for academics. And the sentence, or one of the sentences that we provided in this prompt that limits or intended to limit the scope of the tasks that the chat was doing was, your target audience or your users are mostly employees in the University of Frankfurt. And so your answers should be tailored to that university level. Our intention was very pure, but some of you has already detected the problem. We wanted to provide academic answers, formal answers to university employees. The model interpreted this as, there is a Frankfurt in the sentence. Frankfurt is in Germany. These are Germans, so I answer only in German language. And we ended up unintentionally with this problem. So the models actually tried to interpret our data first, cautiously, but their interpretation of our is very much affecting the way they respond. So this is also a risk. There is a risk in the models itself, how they work, their inner mechanisms, their abilities, the roles that they are programmed to do, as we mentioned with Meta, for example. So they are sometimes allowed to do something wrong or catastrophic, and so on and so forth. There is a risk lying in the transfer of this prediction to the users, because users don't always actually get the information that was just predicted. They get a masked or a modified version of this output. For example, if you talk to ChatGPT and you start by a sentence intentionally hate speech, you will get a response that is not the output of the model. It will generate an answer to hate speech. There are rules around this model, the whole system of ChatGPT that prevents this prediction of reaching the users. And this is something that is done manually by developers. And so, can we control it? It's a source of risk because we cannot control those rules. And the last risk I will end up with, this is not the actual last risk, but I will just highlight here the point about over-reliance, the point about how we understand the model prediction, and how much do we depend on that model prediction. And that's a social problem on a psychological level, which unfortunately is now also materializing severely, especially with those who are growing up with this technology. We know what it means not to have ChatGPT. Some of us, including me, know what it means not to have Google. So it didn't have any way of researching anything. We had to go to libraries and search for information. We know what it means. And so we use those technologies. It's different from a child who's just aware of this technology alone. They don't know how to actually take the long way to reach an information. They are given the shortcuts directly, and only the shortcuts is what they are aware of. So that's a hidden risk. Now, there is also a risk that we have to address. I'm not going to talk about, but it's very important for all of us to address when we're talking about AI systems. And this is the risk for AI systems. We have teachers teaching students in classrooms. Human transfer is also risky. There is a lot of problems that come with that risk from a human perspective itself. So solving the problem with technology has a social and human level to it, not only a technological level. So in this talk, I'm going to focus on this. I'm not sure why this is appearing again. So I'm just going to cover the knowledge representation risk, the mechanism of the model itself, and the risk of actually interpreting this data and making a decision based on it. So a check for time, and I have to hurry up. The first one is then the knowledge representation risk. Knowledge representation is how to actually distill human knowledge in a way that machines can understand it, make use of it, be trained by it, etc., etc. And there are so many ways to do it. Models are a way to distill human knowledge, like decision trees. Ontologies are a way to distill knowledge. There are logical operators to represent human knowledge, and so on and so forth. And today I'm just going to highlight which is knowledge graphs. Knowledge graphs are networks of interconnected entities. Entities can be actually anything. This is, for example, a knowledge graph for a person watching a movie. The movie has a tagline, is released at a certain time, it has a title, the person has a name, was born in a certain city, and so on and so forth. This is an actual knowledge graph of this. So this is the base ontology for the knowledge graph, which tells you which entities are there. We have a person entity and a movie entity. Here is the actual data. This is the Star Wars, if I'm not mistaken, and Spook, played by Leonard, for example, and so on and so forth. When we present the knowledge in this network structure, we gain bits that enable us of actually making logical predictions and logical connections between the different entities. One of those connections is the similarity. If we have two people working on the same set, then they might share something in common. If we have two courses being taught in the same university, then they might be highly recommended to you if you're attending that university. So this and transitive relations in the knowledge graph can be used to make predictions, can be used to make actually interpretation or inductions. The graph is basically built with graph nodes, connection, which are the entities, relations between those nodes, and properties for both nodes and relations. So, for example, you can see is a property of that person. It's not an entity of its own, but it can be an entity of its own. And this subject predicate object is the entity connected to entity triplet, which is how knowledge graphs are then automatically represented in a machine readable form. Machines can read those triplets, can actually make deductions based on them. So the two use cases that I'm going to govern have been in two different scenarios. What is the context of the first use case, which is knowledge transfer industrial application? The case that we have faced is basically transferring knowledge from engineers who have been years and years to those new engineers who are just joining the company. In many cases, the engineers who have a lot of experience leave this company, and there is a very difficult time to actually wait until you train a new engineer, until that engineer gets the experience to solve problems in that industrial context. And so what we were thinking of, or what we were asked to provide a solution for that industry, is basically a way to represent the human knowledge, the experienced engineer's knowledge, in a way that we can transfer it to the new engineer. So that's the context. And we tried to solve this through semantic knowledge representation, and we built a knowledge graph from all the documentations that experienced engineers have produced. They have produced product specifications, they have produced failure reports, and they have produced failure repairs. So when there is a failure, it's tested and repaired, and all of this is actually documented. And so we tried to build a knowledge graph based on that process. We analyzed the documents in that industrial setting, and we have this production and test. As I mentioned, there are failure reports in the testing, and all of these documents are then translated into types of reports. Cases, specification documents, and hierarchical information about the order of modules in a certain product, for example. And we tried to create a knowledge graph from it so that we can present the old engineers' knowledge in a semantic way, and then an engineer to search easily for a solution for the problem that they are facing. That the knowledge graph will documents that are relevant to previous solutions of the same problem. That is basically the intention. The knowledge graph looked like this. We have failure cases in the back notes. We have specification documents, and we have hierarchical structures. Now, to connect all those documents to each other, what we try to do is to analyze the vocabulary document and extract that documents to each other. Now, I'm not going too much in detail for the technical due to the time, but one of the approaches that we have used is n-grams. N-grams are terms. One word, two words, three words that happen in the document or are mentioned in the document. And we try to analyze which document actually have certain n-gram, which is bigram or bigram or unigram, meaning one word, two words, or three words. And the assumption was if two engineers will document the same solution, they will most likely use the same terminology to actually document that solution. Well, that assumption was to some extent correct intentional level, but on practical level, we found that engineers in different units of the company use different codation forms. They use the same component names, but they represent the problem in a different way. For example, if we have a low voltage on the input circuit, one engineer would say, low voltage input head is blinking. Another engineer will write TR to V0, and those two are the same thing. They are both a low voltage on the input circuit. How can we actually detect that? So the lesson that we have learned from this particular implementation is we as technical developers, we cannot find out all the information about the similarities in the text without asking the engineers themselves. We usually take the data, analyze it roughly, clean it, provide it to our models, and generate a prediction. We did this, and we used the BERT model at the beginning, and we got wrong results. Very low accuracy in the results. We thought we go more complex models. We used SBERT, and we got even worse results because the engineers don't even write sentences. So we went to basic TF-IDF or term-based approaches to find similarities, like, for example, the n-grams or TF-IDF, if you are familiar with it, but you don't need to be familiar with it. And they performed well. And then we went and looked at the data and found out that the ways engineers are writing the documentation is very much different. So what does that mean in our context? It means that the design process of the AI solution cannot happen only from the developers. We need to include stakeholders from the very first stages of the design in order to understand the data, to represent the knowledge, and to find the technologies that can work on that level of knowledge and select the models that we are using. So just to recap, or to finish this case, there are transitive relations between those different types of documents. And what we did is actually building a system that understands the documents based on the input from the stakeholders, and then creates a knowledge group and provide the documents in a search engine. So we handle the domain-specific information retrieval and human-computer interaction for efficient interaction with the users, making the search easier. How do we make the search easier? Well, we actually try to provide textual and visual explanations where this search result comes from. The explanations showed a graph, which is a subset of our knowledge graph, to the design engineer, which enabled them following the process or trying to understand the process, how this document is related to another document, and which the reasons, for example, which n-grams, which vectors are used to connect the documents to each other. We didn't make a prediction. We just retrieved information, provided it to the expert. The retrieval was not very accurate. The expert's ability to actually at this list of results at the end and say, this and this and this is useful for me. So this is kind of a collaboration between the AI technologies that provide results, not necessarily very accurate, and the human intelligence, which actually is able to make better decisions and select or filter those results in a very quick manner. That only works if the user is an expert who can filter those results. So okay, I will jump through this because this is not too much. So what happens if the user can tell if the retrieved results are accurate or not accurate? Like students, if you provide them information, they cannot say that this is actually suitable for them or not. In many cases, sometimes they do, but in many cases, they don't. So the second use case that we have highlighted is vocational education and training. The context in which we were working is nursing education. And nurses in general have a lot of training, which is military training in their workplace, but these training programs are very much limited to courses or one topic. So what we try to do is to connect these topics to each other and relate it to a real life situation. For example, if you are working as a nurse in an elderly home, and one of the elderlies has dementia and they refuse to take a bath. This is not only knowledge about what dementia is, it's not knowledge about nursing and how you medically treat a person. It's not only knowledge about how you communicate with a person, it's a knowledge about this together so that you know how to apply baby talk with a person with dementia, for example, and to know about the regulations if you skip a bath or maybe skip it, and so on and so forth. So this complexity of the problem needs a connection between different disciplines and providing a solution for that problem. And then the training should be pedagogically oriented. So this is our context. Why is context important? So let me ask you this question to see if learning context at all is important, which will justify why we actually embedded that context in the knowledge graph. How many of you look at this figure and say this is number 13? How many look at this figure and say this is the letter B? Okay. Now, how many look at this figure and say this is the letter B? Okay. So now how many of you will say this is letter, this is the number 13? But in a certain context, the same entity changes what you mean. And it is not just figuratively, but also literally. Nurses who are working in elderly homes, they need education which is different from nurses working in hospitals because they have two different types of nursing. Their context implies what types of recommendations we need to provide them. And so we need to understand that context before providing the recommendation. And then distill that context in a way that machines can understand, our model can understand, and then train the model or use the model to generate a prediction, which is in this case a recommendation for learning. So we did a survey what a learning context is. Learning context is basically the situation in which learning happens, and it's described by certain factors. So we took that definition and we tried to extract those factors. What factors describe my context as a learner? Well, there has been recent surveys actually found 218 factors contextual data, like the way based on ranking, the time available for learning, what technology and so on and so forth. And so we tried to analyze those and select those that are very much relevant to our nursing domain. And we selected top 3, the background knowledge, like what previous programs, bachelor programs that you have studied as a nurse, and the time available because you are learning on the job, so you have very much limited time. And the preferences, if you want courses, if you prefer videos, for text, and so on and so forth. And we analyzed those and tried to find a way to embed them not only in the knowledge graph as a data structure, but in the reasoning of the models themselves. The way we did this is that we started by creating the knowledge graph to embed them structurally in knowledge. Our curriculum was composed of this tree, a journey, which is the final learning, has several courses composed of several topics, which are groups of educational resources and the actual open educational resources, the OERs. And our goal was actually to connect those on the course and topic level, to change this tree into a network, which is the knowledge graph. And that's what we did. And we actually used several text and NLP approaches for this, utilizing the textual content of those courses. In our case, it was the titles and descriptions who had the richest textual content of the courses. And we analyzed them in 2 different ways. We detected the languages, then we processed the text, cleaning it from language that is less important, and then we created the embeddings, which are to change words into numbers that we feed it into the machines. And the embedded vectors were in different languages because we were handling 2 types of materials, in English and German in our use case. And then we did a translation simply through DeepL, and then we cosine similarity between the title embeddings actually, and then we detected if these 2 titles are similar or not. For the descriptions, they had much more text, and so we actually did a topic extraction step to extract certain topics from this course description and understand what topics does this course cover. And the topics themselves were then compared in a matrix, again, through embeddings, and the embeddings were handled by multimodality, or the multimodality of the embeddings was handled. And then we have a cosine similarity, which is aggregated over all these projects and averaged over those topics and averaged to find the final similarity. Then we ended up by creating, this is the actual or part of the actual curriculum. We have courses about dementia in elderly care, communication in elderly care, which were actually parts of several trainings, completely separate trainings. And we tried to connect them through the structure in one potential knowledge representation for a potential training. And from that, we can find that now these yellow connections, which have been found by the textual similarities, enable us of actually producing a learning recommendation, which includes material from several parts or from several trainings. What we also found is that there are areas of this graph that are densely connected. These are topics that happen in different trainings, but they always happen in the same context. And so this structural or the structural property is actually representing a certain context in this learning domain. And that is information that we gained structurally and not from the data itself. So how do we use this? How do we combine the information that we get from the representation structures with the models that are working on those? They are models like networks. We try to use the approach of neurosymbolic AI. It is neurosymbolic AI. Simply to those of you, if you are not familiar with it, AI is the one that depends on neural networks by this definition of neurons connected to each other. And then we have machine learning, deep learning, based on neural networks. So that is a specific type of AI using those neural networks with their topological properties and mathematical properties, for example, the training processes and so on. Symbolic AI is more on the side of systems, expert-based systems, symbolic representation of knowledge. How do we, for example, represent a sentence in logical operators? And that symbolizes our knowledge. And the predictions or the training made on that type of data or representation is a part of symbolic AI. Remember when I told you about these triplets, like a person lives in a city, I can use this or this triplet to answer a question, where does this person live? And that's symbolic AI. Some people don't like calling it AI, especially some of the controversial AI like fuzzy logic and so on. We're not going into that discussion, but I'm from the party that still believes that symbolic AI is strong for the reasons I'm also showing you today. So what we did is actually building a framework. It's features of both. At the center of this framework, the symbolic representation of knowledge, the semantic representation of our knowledge, which is the knowledge graph itself. And the knowledge graph is constructed from its relations and nodes. How do we define these relations and nodes? Well, we start by analyzing all sources of knowledge or information that we have, data and information. We have data coming from domain records. We have data from or information from information sources, databases, and so on. And we have rules that are defined by the experts. For example, when they tell us how they document failures. The next step is actually as we have seen in the both use cases, and then connecting it to the new part of AI. And this can be algorithms, for example, recommendation algorithms. They can be neural networks or otherwise. The explanation algorithm, which can be also of the neural AI and so forth, and so on, connected to the users through requirement engineering. This structure has been proposed around 2022, and after the large language model, you hear a lot about RAG systems, retrieval augmented generation, which is based on the idea. I'm not saying that we founded RAG, no. I'm just saying that this is not new. And there's been a lot of for RAG to actually utilize local data, clear information to influence how the models are working. One of this spectrum of works is our framework. And I'm not saying by any means that it's a base of RAG or something, but the logic of RAG has existed for years and years. And now it's actually just gaining a lot of momentum because LLMs are giving it that momentum. But the idea of using data or knowledge to actually influence the predictions is very well known. So how do we create this recommendation over the knowledge graph? This part includes then how we embed contextual factors, not only in the knowledge representation, but also in the mechanisms of the models that are generating that prediction. The model that we are using to generate the prediction, if this learning is suitable for you personally or not, is Markov decision process. Markov decision process actually represents, so this is a representation, this is not Markov decision process yet, sorry. This is the representation of the learner, context in which this learner exists, like what courses they have studied, this is the background knowledge they have, what the course that we have seen, or the course knowledge graph. And the idea is to generate a learning recommendation from the context to their final goal, which OERs should actually be selected for them. And we can see in the network there are very high number of potential paths to be recommended. So how to select those paths? Markov decision process is a process to make decision under uncertainty. Okay, well, I don't know which path I should follow. So Markov decision process can actually give me a ranking of those paths. Think of Markov decision process as a way to escape a maze. You try the ways and then try to remember if one way led you to a dead end or not. And then you try another, and then you rank those ways to find your way step by step to the exit. And this is how Markov decision process works. We have a state, actual state in which we are, and potential transitions to future states until we reach our goal. And as a virtual learner explores potential paths in this network, it gives them ranking. This path led me more quickly to my goal. This path led me more effectively to my goal. And then quickly or effectively are the factors that we use to actually give weights and importance to the different paths. And we use them to personalize. So we remember we had the three factors: background knowledge, preferences, and time. And these were our weighting factors, which you reach your goal based on the background knowledge, based on the time and your preferences. And we developed a function that actually embeds those factors algorithmically in the reward function of this Markov decision process. So Markov decision process is based on a reinforcement learning, an agent exploring this graph and giving ranks to those paths. How those ranks are generated? Well, we have the reward that is provided to a certain move from one state, from one course to another course, or from one state to a future state. And we have potential for deviation. Then the ability to make a decision, just like a normal learner, they get a recommendation, but they might follow that recommendation, and there is an option or potential that they will follow another path. And so we embed this, the reward that you get from taking the full course, and the potential for you to actually explore automatically in the reward function or in the state value action, we call it, which gives a ranking to a certain move. So the idea is that we build a reward function based on those contextual factors. These are our context factor, background knowledge, and time available, and exploration factor, which is the preference, represented mathematically so that we can influence how the digital learner, the virtual learner, is actually giving weights to a certain learning path. This way, we actually not only embed context factors in the data structure itself, but also in the mechanisms of the model. So algorithmically and structurally. And with those two working together, a neurosymbolic AI system can generate potentially recommendations that not only have a level of accuracy because they are tailored to the user preferences and background knowledge and time and so on, but they are explainable. We know exactly what the algorithm gave a certain ranking because this value is calculated mathematically. We know exactly how this value is calculated because we do have the function, and we do this value is generated a certain number. So we can actually explain to the deepest detail how certain ranking has been generated for the model, not just statistically, but explicitly. And we know the knowledge data structure, the knowledge graph, and those courses are connected to each other. And why? Because their titles are similar, because their description have two topics similar to each other, and so on and so forth. And from that, this information iteratively to link all this in the knowledge graph and find at the end the ultimate path that leads us to our goal. Now we have generated the calculation, is generated, we want to explain it. And therefore, comes the role of explainability and user agency, which is the last part of this talk, and I hope I can cover it. Oh, running out of time. So I'll try to go through it as quickly as possible. The part, as we normally give to a student, is a list of courses to follow. In the knowledge graph, however, this part is different. It is complemented by additional information like the structure of the courses to which elements belong. We have similarities to other courses in the knowledge graph, and we have areas of condensed connections. As we have seen in previous knowledge graph, they represent a certain context of a learning topic. And we use all this information to actually generate a final recommendation. So I'm going to generate the explanations, and I'm going step back to say how explanations are generated in general, so that you can select the explanation approach you would select for your systems. Our system actually takes this information from the knowledge and extract rules and definitions from the experts themselves, again, embedding or integrating domain experts in the very first stages of the design, the explainability of the system, of the data, etc. That was essential learning that we have gained after these 7 years. We would never now start designing a system from the developer side alone. And they're taking into consideration the learner perspective. In this case, we are generating template-based explanations, which extract information from the model, extract information from the data, and then generate a template. This course is suitable for you because these elements of the course have been found similar to each other because their titles are similar or topics are similar. And the ranking of the model found that from this course to that course will give you a better suitability because it fits your time. Again, because this number was generated from the time factor. And then we fill this information in the template, and we use OpenAI chatbot. At the time, we were using models to generate a better phrasing. The whole use of this model, the LLM, is just to phrase. It's not to generate facts. It's not to actually find out why these courses have been recommended. It's not to find out why these courses are even similar to each other. All this information is something we already know. And the model now task is just to phrase that explanation in a way that the user can understand it in a better way, can comprehend the data in a readable matter. So, limiting the scope of LLM was essential for us to avoid generating misleading information, to avoid generating less accurate explanations, and so on and so forth. But then, again, utilizing its ability to phrase information in a nice human readable way, in a natural language. How can you generate your explanations now? The question is how to generate explanations at all. So explanations are basically different from each other based on the systems that we are explaining. Some of the systems are simple, and some of the systems are very complex. And yes, I feel like a coffee, so I usually use that example. So the open book systems are the systems which we know their mechanisms, which they work, like the Markov decision process, for example. A neural network, on the other hand, is a black box. We don't know exactly what's happening, but it's very difficult to explain it, especially to those non-experts. And so we call it the opaque box. So it's difficult to see inside. The key difference between explaining these two types of models, the open boxes and black boxes, is the data we get. From an open box model, we get data from the input. We know what is the input that we are feeding to the model. We know what is the output. We see it, we touch it, we measure it, we test it, and we know the parameters of the model itself. We know the pressure of the coffee machine, we know the water temperature, and so on and so forth. And all this information, all these features are collected from input, the model, and the output to generate an explanation. The black box model, on the other hand, we don't easily reach inside how the features are functioning. And so we use only the information from the output and the input to generate an explanation, which is limited, but still possible. So, explanation is divided into these three levels. Basically, the data that we're feeding, the model itself, and then the prediction, which is the output. In the data, we have explanations about the data collection, the data processing, and the data interpretation. as we have mentioned in one of the risks earlier. The model itself, we have the training approach that is used for this model. We can explain what training approaches have been used and so on and so forth. We have the structure of the model, the topology of this neural network. Does it have certain layers at the end? Does it have convolutional layers and so on and so forth? What does that mean for the output? In prediction, we have the assumptions made for that output. We have the assumptions made for the training data and how they reflect on certain predictions at the end. The content of that, the context of that output as well. The format of the output, the accuracy of the output, we can sometimes measure and so on. Then there is something missing. And this is something very important. Where is this prediction going? This prediction is going to the user. So from the user perspective, we are talking about not just generating an explanation, but generating an understandable explanation. Remember the 3 tiers. We can generate very high technical terminology to explain a model working. But is that what we want for a student? A student doesn't need to understand how the model works. They need to understand how this recommendation is suitable for them. End of story, which is not related to the model working at all. So we need to think about understandability of this explanation and the prediction task to the target audience. And here we talk about causality. We talk about fairness. We talk about bias, and so on and so forth, which are components of the explanation that we need to take into consideration when we're handling an educational context. So I'm using those terms: explainability, interpretability, transparency, exchangeably. And it's not only my fault. Unfortunately, in the literature about explainable AI, there is a lot of mix between those terms. And to some extent, they are used interchangeably, which is wrong. So recently, they're doing a lot of work, of which we are doing, to actually disentangle those terminologies from each other. And we follow one of the definitions that are very well founded in literature at the moment. And those definitions are as follows. Explainability is then the fact that you can explain or generate an explanation, like a description of how it works, in a way that a user understands. So the explainability is an active concept. To generate it, you have to find a way to make it understandable for the user. Interpretability, on the other hand, is a passive concept, which is not negative. It's actually a good thing. Interpretability means that itself can be understood, can be interpreted. So a model is interpreted if you can simply understand it, like a decision tree. If-then rules, they are interpretable. A neural network is not interpretable because you cannot generate an understandable explanation from it, at least not out of the box. And so it's a passive concept. It can be interpretable or not. You can make it explainable if you put some effort actively. Transparency extends beyond the model, and it covers the whole process, from collecting the data, storing the data, cleaning, roles, choosing the model, hosting the model, handling the security of hosting the model, generating the prediction, masking this prediction, adding rules, etc., etc. The whole process then is either transparent or not. Transparent means that you, as a user, knows what's going on. Do you know how ChatGPT 5 was trained? Do you know how Llama or Llama models were trained? Well, sometimes yes, sometimes no. Sometimes we have the data sets that were used for training those models, and therefore they are transparent to some extent. We can detect if there are biases in the data. For models, they are trained on scrap data from internet, and we don't know the limit or the amount of bias. We know there is a bias, but we don't know the limit or where exactly it is. So transparency is the process of actually understanding all of this. And you can see that those generate different types of explanations. Some of them are explaining the whole data set, like every student in the school will get most likely something. A specific student in the school got a certain prediction, which is the local explanation. This is also available in the presentation. And I just wanted to show you one difference between global and local explanations, because this affects the decision makers in higher education and other schools. So for an administrator, user, or stakeholder, they need to understand holistically how the model reaches a certain prediction. They need an overall picture, and therefore we give them global explanations. We show them all the features from all the students that we have in the school, and say, well, the attendance feature has a lot of effect on the predictions. And therefore, if your students are attending, they are higher likely to actually stay in the school. If the attendance is less, is much less than others, they are much higher likely to drop out of school. And so we try to see which features the model is actually using to generate a prediction over the whole sample of students. And this is a global explanation. Local explanation says Mark drop out 70% out of school because this and this and this, because of his age, because of something else, whatever. So we understand the feature effect on the final prediction on a very local and individual level. And that's useful for Mark, for the student himself or herself, to understand why am I recommended to attend better, although I like watching videos at home. So understanding that, okay, this might higher likely drop out, I can make a decision as a student and say, that's nonsense. I watch the videos regularly at home. I don't attend all the lectures, but I watch the videos regularly. So the prediction you are providing me is useless. I can make a decision about it by understanding how the prediction was generated. And that's our goal. That's the message I wanted to reach from today. So I will jump through these, and I will show you that once we provide those explanations through interfaces, proper interfaces to the users, they can actually control the prediction of the model. And we need to provide them with that level of control. We give them that agency to actually change their profiles, change the model features are given different weights. Mark, the student, can go to the teacher and say, your model is generating false predictions of me getting out of school because I'm watching videos offline. I'm not attending, but I know what's going on. So when you go to your model and change some features inside, and this is not the task of the student, this is the task of the expert who understands that from explanations, local or global, and make changes to the model mechanism, to the inference from the model that the model is doing, the data collected, to the features that are extracted from this data, when you reduce the amount of features of certain data in feature reduction approaches, and so on and so forth. And all of this can be changed and controlled once we have explainability, once we understand how the model is generating a certain prediction. So this is a multi-dimensional, and I have repeated multi-dimensional term a lot today, but actually explainability is, not unfortunately, is like that, whether we like it or not. It has a pedagogical element. What is to be explained? How much information do we provide? What is the shape of the explanation? Textual, visual, etc. It has an evaluation perspective. We need to evaluate if this explanation is actually providing any usefulness for the user, not just for the sake of providing explainability, but looking at the final ability or final goal, which is to make a better informed decision. We have the stakeholders who are responsible for generating the explanations, who are receiving this explanation, who are handling the system based on the feedback, and so on. And this design aspect of the explainability, what is the content, shape, and so on, so forth. So I will end up with one concept of human AI complementarity. And this is a concept that Professor Gollam is now also researching very deeply. I'm grateful to the chance that I have worked with Professor Nutli on explainable AI and understood how he actually looks at the AI interaction from a different perspective and has some considerations against the word collaboration or the word partnership and so on and so forth. I'm not saying this is the correct thing. There have been some papers about human AI collaboration in this conference, which were brilliant, were nice, they have very nice approaches, and so on and so forth. But thinking about human AI collaboration, we need to think about the accountability, about the level of responsibleness or responsibility that each of those parties have. And so you can check the paper, but to summarize what Professor Jukova is talking about is that the amount of automation that is on AI to generate a prediction against how much a human is able to control that prediction leaves us with 4 different regions. For per region, where we can automate a task and the human has no control over it, which is the worst case scenario. When we can automate a task has lower control over it, we have a lot of risk because the AI is making an interpretation of the data that we cannot control, and that's risky, which is something that technical developers don't like. Less automation and higher control is something pedagogical experts would like to have more control, but then the automation means that they have to spend a lot of time in analyzing the scores and so on and so forth. And so here the humans internalize the prediction of the AI. They try to understand it difficultly because it's not easy to automate, but they put a lot of effort and they can control as an outcome from that effort they put. The situation that we're trying to reach, but we still haven't reached, is a system or a space where systems can be automated, like automatic grading systems, to a higher level, and at the same time, we have a higher level of control over them. And for that, Professor Gollam says that we need to develop the model of the human and a mind model of the machine. A mind model is how to describe the thinking processes. And we so far think of how to describe machine thinking processes to humans, but we also to think how to describe human thinking processes to the machine. And perhaps as the machine interprets in a better way how humans think, machines can generate better output. So with that, this is the system that we have developed, type of explanations, taking into consideration the stakeholders. And so this is to skip, but you are welcome to see the charts that we are developing for conversational explainability, or perhaps ask me about it if you are interested. The evaluation is also something we can discuss or we can check. The takeaways I wanted to leave you with is basically that representation of knowledge is very essential for us to enable the models not just to generate a prediction, but understand how we think, how our data is processed, and try to mimic that process in generating a better responses. We need symbolic features in our systems because they provide us with transparency, like transparent knowledge models or transparent Markov decision process. But we still need the stochastic abilities of the models themselves. The ability to analyze huge amounts of data in short times is something also advantageous, but we combining it with transparent data structure can actually perhaps reach a level of interpretability. What do you think about the explainability? It's not a question of why a prediction is generated, it's a question to whom this output is generated. What is the content of this explanation? What is the method used for this explanation? And who's receiving that explanation in the first place? And with that, we can make a better decision. And one decision that I would like to think about a lot is not just how we use AI, not just to which extent, or what AI we are using, if we are using AI at all. What is our goal of AI? Should we AI or so? The question is to AI or not to AI. And one of the goals of using AI is also I'm sorry. Okay, I'm really sorry. So the quote I really like and very close to my heart is, I don't want AI to do the thinking and image generation art so that I can do the dishes. I want AI to do the dishes in my laundry so that I can think and read and do art. And perhaps with this, we can think of our use of AI and when to use it and when not to use it, especially when we're asking our students, our peers to also consider using it or not using it. Thank you very much. I'm smiling because I usually always go over line. And I was like, today I have 80 minutes. I can never go over line. Well, that didn't happen. Sorry for taking much time.
Thanks, Hasan. I don't know who is first. Okay, maybe I can come from there.
Thank you so much for an outstanding talk. I really enjoyed it, and I love the topic a lot. And I wanted to challenge you with a question on biases, of course. We talked a lot today, you talked a lot today about biases of AI models, but humans also have biases, as we all know. So I wanted to challenge the concept that you introduced, the idea that you introduced, that we could have a domain expert actually impacting the weights of the model when it's making predictions, before it's making predictions. Don't you think there's a high risk of introducing even more bias in that case?
Definitely. That bias is something we can see, touch, and measure because we are interviewing that domain expert. And we can look at the answers they are providing and perhaps ask another domain expert, do you think this is correct or not? The problem is with this mass production of data where we cannot easily detect which web page was used to generate that input, which word in my two-page prompt was used to generate only a German answer at the end. And so it is, of course, there, and it is inevitable. And this is one of the reasons why explainability also, in my personal opinion, is important, because biases are inevitable. We cannot actually generate something objective. This is simply impossible, because we are biased, like you mentioned. And a biased entity cannot generate an objective answer, philosophically speaking or logically speaking. Maybe you can find a way, but I am not aware of a logical method to actually reach this. But again, with distilling the information from individuals and analyzing that information, addressing that there must be a bias there, you are approaching the prediction with a much more informed way. I know the prediction is not 100% suitable for me, definitely. So how can I critically think about it? And how can I evaluate if this prediction actually helps me or not, or to which extent it will help me? From this long learning path, which we recommended to our students for following for 6 months, this is a huge investment of time. And in our testing, one of our users got into the test. The test was for 4 hours, of course, just a small experiment of the 6-month learning path. And the test was for 4 hours, 3 of which were for learning. So they have to stay in the same place for 3 hours, doing learning, watching videos, answering questions, etc., etc. One of the users finished after 1.5 hours, and she was bored and she wanted to leave. As simple as that. We had interviews. We asked the nurse, why did you use so much little time? And she said, everything was amazing. I got the explanation, and I understood why the recommendation is not suitable for me, so I skipped half of it. And then so passed. And we thought, okay, the system is less accurate, but it's fulfilling the goal of what we want. We want to enable the user to make a better informed decision for themselves, and that's what happened. So we're very happy with this skipping of the content, because our goal is not to force the user to follow the path we recommend, but to enable them of making a decision about it. And so it's the same with the biases. If we tell them our recommender system is biased, they will think about it differently. And so it's a way to actually address that bias, or use addressing that bias in thinking critically about the recommendations or the predictions. You're right, it's inevitable.
Thank you so much.
Thank you. Thank you so much for your very interesting presentation and demonstrated points of use. And it's very important approach, because if we don't know what is in black box of artificial intelligence, when it's very risky to use this decision without understanding of its reliability. For example, if we have quantity data, and you demonstrated, for example, example of dropout for students, when we know most important factors which can impact on this, when we can prevent this. But in this case, we can use, for example, SHAP or LIME methods to understand most important factors. And my question concerns to textual information. You told what context is very important, and to whom this information is conveyed is very important. So in this case, we know, for example, if in quantity module we delete some factors and, for example, error will increase, then this factor is important. But how we will know in textual queries, for example, it's enough information, is underestimated or overestimated information, and how can we measure it's enough information or not to understand it's a reliable decision or not?
Thank you very much. That's a wonderful question. And for those who are not familiar with the Lime and Shapley values, they are, you see those features that tell us that the dropout is based on attendance. Shapley values or Lime explainability approaches try to generate a score. For each feature, it tells us, okay, attendance is 70% important, or the number of courses registered in one semester is 50% important, and so on. So just to mention this, and this is a very important aspect, which is now automated to generate explanations on the feature level. Tell us which features are more important. The figures that I've showed are Shapley values. Actually, they are visualizations of Shapley values. So to your question, handling text is very difficult. I'm not the expert here. We have experts in NLP, and they can tell you how fluid this language is and how difficult to actually measure something on a lingual level. It is possible by masking some of the terms and seeing how this masked input sentences will generate an output, whether it's wrong or not, or other approaches from NLP. But I would argue here that it's not only finding the features in the text that's important itself, but also understanding the semantics of the text. So I'm not looking in the input text what term, or I'm not always looking what term has been used to generate a certain output. I'm looking for this, but not always. I'm actually looking for the relation between this term and other terms in the sentence. When I have a sentence that have a negative sentiment, the sentiment itself, which is my positive or negative attitude in that sentence, the sentiment might be the important factor for me, not the terms used, the word not, or the word, any word about sarcasmic approach or a sarcasmic expression or so on. So yes, it is very difficult to measure. There are some ways to actually understand on the word level the features on the words themselves or words in sentences. They are not as accurate as analyzing a feature that has a certain scalar, a certain number of it, but they are also effective. I would say, again, I'm not the expert. I cannot say a lot of, but we did some masking, for example, to find out if certain terms used in the student question are affecting the user, like the word Frankfurt we used in the prompt, for example. Some of our users used the word critically in their interactions with the model, and it affected, just the word critically, it affected how the model is actually thinking, how much the model is thinking. This is something you see now if you test with GPT-5. It thinks more if you use such terminology like accurately, critically, etc., etc., just because you use the term. So we can mask this term, omit it, and see if it has an effect or not. But then again, we need to understand what features we are looking for as well. And when we find out which features we want to extract, perhaps we don't need to go all the way down to the word level, but have a sufficient explanation from a higher level of features. I hope this answers this question.
Thank you very much for your enlightening talk. Enjoyed very much. Found several places where we did similar things. But now I would like to provoke you. Could you please return to the previous slide where, yeah, this example. I do see two things here, which are related first to user perception in terms of, so to say, over-humanizing AI. And the second facet is more about fairness from the viewpoint of AI, so to say. So now the question is twofold then. The first part is to have any ideas about how to train and improve user perception in order to demystify AI and not to treat them then like a human-like intellect, but like an instrument. And second is, if people do continue over-humanizing AI, what would be the feedback in return from the AI side? Are we at the eve of the AI rising?
Nice. I really appreciate those questions, honestly. All the questions were really nice, and I do appreciate having this discussion. These are two of the topics that I spend a lot of my time thinking about, not because they are very or without answers. They have this philosophical aspect of them, understanding how humans process tools that we are using to, like you mentioned, overhumanizing AI. So to the first point, our utilization of AI might be looking back at history. So the direct answer is I don't have a solution for it. I don't think at the moment there are solutions for it. But the way I would approach it, or I have approached it, is looking back to history, to other revolutions that are similar to, for example, the LLMs. Look at the beginning of AI hype itself in the 70s, 60s, and 70s. Other technical revolutions like the use of computers as tools for computer-aided design, for example, for calculations, and so on and so forth. Of course, the scalability is different. If I go a little bit further back, we look at electricity and how it changed our perception of a moving vehicle from steam engines to electrical motors and so on. Having lights, being able to read at night altogether, etc., etc. So we can perhaps find traces of how humans perceive those tools. And it's just a personal opinion about it, but I think that as long as we are within this hype, we continue overhumanizing because we are just fooled to some extent in a positive way, not in a negative way. We are kind of misinterpreting the capabilities of those tools and are giving more than they deserve. But look at how we started using ChatGPT in 2022. To ChatGPT, we asked a question, generate a recipe, or tell me how to write a proposal, project proposal, and it wrote a project proposal. And you were mesmerized with that it is now the tool, it is the answer. And then when we looked at that answer and we looked at the papers that it referenced, we found that it was completely made up. And so by analyzing the answer more and more, our trust, our dependence on this AI gets lower and lower. And so the more we live with AI, especially with the help of LLMs, the more we get accustomed to their limitations and abilities. And I guess at some point we will reach, after the vibe, a stabilization or a saturation level where we as humans are better able to judge the abilities of AI. So I don't continue this exponentially, or at least not linearly. We will go up and then we will go down to when we actually are accustomed, when AI is actually responding to us when we turn our washing machine and when we go back home and we switch on the light and off the light and so on and so forth. We don't overhumanize Alexa, although at the beginning we had, let's say, talks with Alexa and Google Assistant, just because having someone to talk to was really nice. And then this is these chatbots and are using it just to, let's say, let out steam and get less stressed by just talking to someone. But at some point, Alexa was just a device in the corner to switch on and off music to many of us. And LLMs perhaps will reach that level. So that's my perception of it. The other question, I didn't understand, didn't forget it, whether we can measure, if I remember correctly, the level to which we depend on AI, or that's also a very nice perspective because it touches on this human AI complementarity. AI systems have, not like we understand it, an understanding of us, not like our understanding of them. They are not cautious entities, but they are statistically cautious entities because they follow stochastics and they follow statistical data processing, and they can actually make predictions. So to some extent, we can say that they have a model of us, an understanding of us, and this is developing. And this will continue to develop. They will better understand how humans think, how humans process information, and they will make us in a much better way. So this is, I guess, is still growing. When they reach a level to make a decision, that's on us. And that's actually my answer to this question. It can be overusing from the other perspective, because the model at some point will handle us so well, it will understand us so well, to the level that we give it the power. I call it, or I guess this is not my naming of it, it's the switch paradigm. We can ask models, when should we switch a nuclear electricity plant, and when we should switch it off? Because the model is measuring levels of uranium, etc., etc. But we are the ones flipping the switch. The model says you should switch on and you should switch off, but we are the ones flipping the switch. And it's on us at which level we will actually give the model the switch and enable the model to switch on and off things. And this is something we are doing at the moment. We are doing it on a medical level in hospitals. Some of the switches are given to models, because they react much faster than humans, not because they think better, but because they react much faster. And so they can save a life by reacting faster. So I guess the answer to this is that this will grow to be responsible by giving the power to the model to actually flip the switch. And the model, regardless of how much understanding of us it develops, it will not reach the level to take over that switch. We will be the ones giving it the power, I think.
Well, thank you very much. I'm also very much impressed by your presentation. And I would like to ask such a question. You see, maybe for the lack of time, you have not touched semantic networks, because I thought when you proposed this title, you see that in case of semantic networks, these symbolic explanations may differ very much. We cannot explain reasoning very well in this case, because in symbolic models, they are similar. They are maybe in some way they simulate human knowledge, yes, processing. And as for semantic network, as for neural networks, I'm sorry, as for neural network, I think the principles of its design are really different. That's why, for example, you embed in this system some explanation model for make it transparent, yes? And if we see in this explanation, we can see that all this is hidden. It is really only input and output. For us, it is not intuitively understandable. In this case, I think this human-machine interaction is almost impossible. What do you think?
That's a really nice point indeed. So with synthetic AI, we do have transparent knowledge structure. So why do we generate explanations in the beginning? But the idea is using these advantages of understanding the human structure, the knowledge structure, to actually inject this understanding into neural networks and try to see from the input and the output of the neural network, in combination to understanding how the data is connected to each other on the input side, for example, what better explanation can we generate? This doesn't mean that the black box will become open. And it doesn't mean that we are generating explanations that are of much higher order than the semantics of the network itself.
Yes.
No, the semantics are there, they are understandable, it's interpretable by nature, but we're trying to enhance how the inner dynamics of the black box are understood when we represent the knowledge on their input and understand the knowledge on their output on a semantic level. So it's kind of combining these abilities from both worlds.
Combining these approaches, but
Yes.
in this case, wouldn't you mean that you will, in some sense, duplicate this model by some kind of symbolic model, not?
That's actually a very also nice point about simplifying models, and that's of generating explanations.
Yes.
a black box and replacing it by a simpler model that we can understand. And this is called explainability by model simplification. The problem with this, and this is a very valid and strong goal, which I also used actually some part of my previous papers. The idea is that we cannot guarantee that the output from the actual black box and the output from the simplified model are 100% the same.
Yes.
We're getting the same input, and they provide very much similar output. The key point here is the user needs. If the explainability you can generate from the simple model is sufficient for our students, so be it. That's very good. And so we don't need to put the time and effort in explaining the black box itself. The issue happens when we generate explanations for example, technical stuff. So have some understanding. And
technical, yes. I think in this case, this user or somebody who uses it needs much more proficiency to understand the logic of the model.
Yes, you are right. If the simple model that you are using also requires technical explanation, you are completely right.
And
yes.
this is human-machine cooperation.
100%.
And I think really it may be very interesting perspective for development of this model. Thank you very much.
Thank you for the insight. That's really indeed the future work to do. Yeah.
Yes, beautiful. Yes, thank you very much.
Thank you.
Yeah, thanks all, and thanks Hasan for your great presentation. I think this is the end of this session, and thank you again for joining.
Thank you very much.